Hi and welcome to this complete topic revision video on enthalpy. Enthalpy can be defined as the heat content stored in a chemical system. It is given the symbol capital H. Enthalpy cannot be measured, but enthalpy changes can. In a reaction, reactants and products usually have different enthalpies. The difference between these is called the enthalpy change, and this is measured in kilojoules per mole. The Greek symbol for uppercase delta is used to represent change. We can see these differences in enthalpy between reactants and products in the enthalpy diagrams shown here. In an exothermic enthalpy profile diagram, the enthalpy of the products is lower than that of the reactants. The chemical system releases heat energy to the surroundings, and the enthalpy change is negative as represented by the downwards arrow. In the endothermic one, the enthalpy of the products is higher than that of the reactants. The chemical system absorbs heat energy from the surroundings, meaning the temperature of the surroundings decreases and the enthalpy change is positive, as represented by the upwards arrow. Standard enthalpy changes refer to reactions done under standard conditions. The standard conditions are 298 Kelvin or 25 degrees Celsius temperature, 100 kilopascals pressure, and for solutions a concentration of 1 mole per decimeter cubed. An enthalpy change measured under standard conditions is given the symbol delta H theta, where theta is used to represent standard conditions. There are 4 standard enthalpy changes that you need to know about in Year 1. These are reaction, formation, combustion, and neutralization. You need to be able to define these and write equations to illustrate them. Let's take a look at standard enthalpy change of reaction first. This is defined as the enthalpy change for a reaction as shown by the molar quantities in the balanced equation under standard conditions. So an example equation for this one could be any reaction really. I've gone for this one, so we've got sulfur dioxide reacting with oxygen to make sulfur trioxide. The enthalpy change is negative 197 kilojoules per mole, and that enthalpy change of reaction value depends on the balance in numbers. So if we halve everything, if we halve the balance in numbers, the ratios in the balanced equation, guess what happens to the enthalpy change? It halves as well. Notice we've replaced the R for reaction for an F for formation. So enthalpy change of formation can be defined as the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. Looking at these 3 example equations, the thing they have in common is that they are all balanced so that they form 1 mole of the product, thereby ensuring they fit with the definition. Standard enthalpy change of combustion is delta Hc theta, and that is defined as the enthalpy change when 1 mole of a substance reacts completely with oxygen under standard conditions. If we look at our first example equation, we've got magnesium solid burning in oxygen, in air, to form a metal oxide, magnesium oxide, which is solid. So state symbols are really important in these enthalpy equations to show everything's in the standard states under standard conditions. Notice this equation could also be used to represent enthalpy change of formation of magnesium oxide and would have the same enthalpy change value since it's the same reaction, because not only are we burning magnesium completely in oxygen, we're also forming 1 mole of magnesium oxide from its elements. Another example equation for enthalpy change of combustion is this one, burning propane. If we look at the enthalpy change value, it's a much larger exothermic value compared to the magnesium one. So that's telling us that when we burn propane compared to magnesium, a lot more energy is released. Lastly, let's look at standard enthalpy change of neutralization, delta H neut theta. And this is defined as the enthalpy change when an acid and base react to form 1 mole of water in the liquid state under standard conditions. And here we've got an example equation. We've got sodium hydroxide reacting with hydrochloric acid to form sodium chloride, and notice we've formed 1 mole of water. And the delta H value is -57, showing it's an exothermic reaction. it releases heat energy. One final thing to note is that for a standard enthalpy change, everything shown in the equation has to be present in its standard state. So that's whatever state it would be in at 25 degrees Celsius and under standard pressure. So that means things like water must be a liquid, and we have to show that using state symbols. That's why they're important. And anything diatomic such as oxygen must be shown as an O2 molecule rather than a separate oxygen atom. Next, we'll look at how enthalpy changes can be measured. Some enthalpy changes can be measured by experiment. This is called directly, using a technique called calorimetry. Calorimetry is the process of measuring heat transfer. There are two types of calorimetry experiment that you need to know about at A-level. The first is called coffee cup calorimetry. This is because it usually takes place in a glass beaker, insulated by some kind of insulating material, which used to be a polystyrene cup. And polystyrene used to be the material used for takeaway coffee cups. Polystyrene has now been discontinued in the UK due to environmental concerns. So other insulating materials that could be used instead of polystyrene might include bubble wrap, cotton wool, or we could place our glass beaker inside another larger glass beaker to add an extra layer of insulation. In this experiment, the enthalpy change of reaction can be calculated, and this involves the mixing of two solutions together, or the addition of a solid to a solution, and then measuring the temperature change during the reaction. A stirrer is used to keep an even temperature throughout the reaction mixture and prevent any hot spots, so that the temperature reading on the thermometer reflects the actual temperature throughout the reaction mixture. The other experimental technique is used to calculate enthalpy of combustion. A spirit burner, which is a burner containing a fuel, a flammable substance, usually an alcohol, of known mass, is used to heat a known mass of water. The water can be in a beaker, as shown here, or in a copper calorimeter, or in a test tube held in place by a clamp and stand. The temperature change, delta T, and initial and final mass of the spirit burner are recorded. So how do we calculate our enthalpy changes from these? First, we need to use a key equation, Q equals mc delta T, where Q equals heat, measured in joules, m is equal to the mass of water or mass of solution in grams, and we need to know the conversion that 1 centimetre cubed is equal to 1 gram for water and dilute solutions. C is a constant, the specific heat capacity, which you can find in your data booklet. It's 4.18 joules per gram per degree Celsius. And delta T is change in temperature, which is in degrees Celsius. After we have calculated Q, we need to convert that into an enthalpy change. The equation for that is delta H, change in enthalpy, equals Q, heat, over moles. Since delta H is given in kilojoules per mole, we will need to divide our Q value by 1000 to convert it from joules to kilojoules. If we are using the coffee cup calorimetry experiment data, the moles we use are those of the limiting reagent. If we're using data from the spirit burner practical, the moles used must be those of the fuel burned. Now let's have a look at some example questions. If you'd like to have a go at the question yourself, pause the video here. This question is about the coffee cup calorimetry one, the one that's used to calculate enthalpy change of reaction. So it says a student carries out an experiment to find the enthalpy change of reaction between zinc, solid and copper nitrate solution. We've got a balanced equation and we've got a method here. So we've got a concentration and a volume of copper nitrate solution. We'll use this to find the moles. It says the zinc is in excess, so this is our limiting reagent that we'll find the moles of. They stirred the mixture, recorded the maximum temperature, and we've got our temperature change here. So we can subtract those two numbers to find delta T. And we need to calculate enthalpy change of reaction in kilojoules per mole and state any assumptions that we've made and give some improvements as well. And this is 6 marks altogether. Let's calculate Q then, the heat energy that is released. and it's going to be released since the temperature went up, which tells us it's an exothermic reaction. So Q equals mc delta T, where m is the mass of solution, so it's 100. Remember, 1 centimetre cubed equals 1 gram for water and dilute solutions, times that constant specific heat capacity, which is in your data booklet, times the temperature change, 38.1 minus 19.5. See what we get. So we should normally get quite a big value for Q because this does come out in joules. We've got 7,774.8 joules. Our next step then is to calculate moles of this. So moles, we've got a concentration and we've got a volume, we've not got a mass, and we're not going to use this mass. So we're going to find moles of a solution by doing concentration times volume. And that is 0.05. You might not have needed a calculator to do that. Then to get enthalpy change, it is Q over moles. And we need to divide this by 1,000 because we want our enthalpy change to be in kilojoules. So 1, 2, 3. It's going to be 7.77 kilojoules of the moles. We get 155.4 kilojoules per mole. So we can either do the mole minus 1 like this, or we can have the slash there. So if we don't have the minus 1, then we need the slash. That means kilojoules per mole. Now there's something missing. Have you spotted what it is? Since the temperature increases, that means it's an exothermic reaction. To show the reaction is exothermic, we have to stick a negative sign on our enthalpy change value. So we've got our enthalpy change of reaction. We've remembered to pop our negative sign on because it's exothermic. We've got our units. If we look at the values given in the question though, the data, they're all to 3 significant figures. So our enthalpy change value should also be to 3 significant figures. So I'm going to round that down. So minus 155 kilojoules per mole. Right, so the next bit then, we've done that. State any assumptions we've made. There's quite a few assumptions we could talk about. I'll show you the mark scheme at the end. So the first one, we can say that we assumed that 100 centimetres cubed of copper nitrate is equal to 100 grams. So we assumed it's got the same density as water. Another thing we assumed was that the reaction was done under standard conditions. And we could also assume that no heat lost to surroundings. And if you want to go for a fourth one, we've assumed that the specific heat capacity of this solution is the same as that of water, which is very similar to this first point actually. Other things we could say include things like the reaction goes to completion, no mass is lost, and that's about it. Now we're on our last point, suggest improvements for obtaining a more accurate value for enthalpy change of reaction. So if we look at our assumptions, we'll get some ideas from there. So one thing we could do to get a more accurate enthalpy change value is we could weigh the mass of our solution. Because it might not be, it probably isn't exactly 100 grams. Or even if it was, maybe we haven't transferred exactly 100 grams from whatever we measured it out in into the beaker. If we look at the method, we can find some clues there. It says measure the temperature. We could use a more precise thermometer that records to more than one decimal place. It also doesn't say anything about the beaker having a lid or having any insulation, so we could say add a lid and insulate the beaker with something like polystyrene or just an insulating material to minimise heat loss. If you'd like to have a go at this next question by yourself first, pause the video here. Let's have a look at this enthalpy of combustion one then. So it says a student plans to find the enthalpy of combustion of propane, C3H8, and we've got this set up here. Here's the spirit burner, and then a bit lower down we've got some data. So we've got the mass of the propane, the fuel, before burning and the mass of it after burning. So the difference in that will be the mass burned. And this mass is the mass that we'll use when we calculate moles, but this here is the mass that we'll use when we calculate Q. And then we've got an initial and final temperature, and we'll subtract those to get our delta T. So first, let's calculate Q. Q equals mc delta T. The mass is the mass of the water that's been heated. And we multiply it by C, our constant specific heat capacity of water, and we multiply it by our temperature change, which is 24.5. Times those together, and we get 10,241 joules. So that's our Q value. Next step is to get moles of our fuel, of our propane. So this time we're going to do mass over MR, because we're going to get our mass from here. It's always going to be the mass of the fuel. We've got a formula, it's up here, C3H8, so we can get the MR from that. So first, let's get the difference here. So 0.242 grams. And then the MR, so we've got 3 carbons, so that is 3 times 12, which is 36, plus 8 hydrogens, each is 1, so that adds to 44. There's our moles. Now we can get our enthalpy change of combustion, which is going to be Q in kilojoules, 1, 2, 3, so 10.24 over the moles. So we've got a number, 1861.8. The temperature went up, which means the reaction is exothermic, so we're going to stick a negative sign in front of that to show that it's exothermic, and the question says it wants the answer to 3 significant figures. So I'm going to give it to 3 significant figures and in standard form. So 1.86 times 10 to the power 3. And we give our units as well, kilojoules per mole. I've just run out of space. Or if you didn't want to give it in standard form, it's minus 1860 kilojoules per mole. The next bit of the question then, so that's the actual answer box. The student finds that the experimental enthalpy change is much less exothermic than the actual one in the databases. One reason could be that the student's experiment had not been carried out under standard conditions. Suggest 2 other reasons for the difference. So it's basically asking us about the errors in this experiment. The main one is heat loss. So heat loss to the surroundings. Because not all the heat given out by this will go into the water. Some of it will escape to the surroundings. And even the heat that does go here, some will escape as well. Another reason is incomplete combustion. So when we do these kinds of experiments in the lab, often you'll see a black substance forming on the bottom of the beaker or calorimeter or test tube or whatever you use to hold your water. And that is soot, and soot is a product of incomplete combustion. It's carbon. Another product of incomplete combustion is carbon monoxide, but we can't actually see that. Values of enthalpy of combustion obtained from experiment are often different, usually less exothermic, than databook values. This is because databook values are obtained using more sophisticated apparatus. This table shows the sources of error and their effect on the enthalpy change of combustion. Since heat loss is one of the main errors in these types of experiments, which leads to an inaccurate delta T, we need a way to correct for this, and this is where the cooling curve correction method comes in. Rather than using our highest and lowest, or final and initial temperature, and subtracting these to get our temperature change, we can find our temperature change graphically by extrapolating, which means extending the line of best fit back to the point at which the reaction started, and this will give us a more accurate delta T temperature change. I have another video that explains step by step how to do this, and I've linked it in the description below. Moving on to bond enthalpy. Bond enthalpy can be defined as the enthalpy change required to break 1 mole of a specific type of covalent bond in the gas phase. We can represent this using an equation. The example equations below show how this would look for hydrogen bromide and chlorine. Notice how we start with a covalent molecule in the gas phase, and then the covalent bond breaks and we end up with 2 separate atoms also in the gas phase. Bond enthalpies are always endothermic since energy is needed to break a bond. This means these will have positive values. Average bond enthalpies are often used in calculations, which will give slightly different answers compared to using actual bond enthalpies. Average bond enthalpies vary depending on the chemical environment of the bond. What does this mean? For example, a CH bond in ethane will have a slightly different bond enthalpy compared to a CH bond in cyclohexanol, for example. This is a limitation of using average bond enthalpies. To calculate an enthalpy change using average bond enthalpies, we use the equation delta H, change in enthalpy, equals sum of the reactant bonds minus the sum of the bonds in the products. Let's practice using that equation in a couple of exam questions. It says that hydrogen can be made by reacting ethanol with steam, as shown in this equation. And it's drawn out the reaction showing full displayed formulae, so that's normally something I recommend doing, showing all atoms and all bonds so we can see exactly what we've got so we don't miss anything, and we've got all the values for each of the bond enthalpies here in the table. And it says calculate delta H. So remember our equation when using bond enthalpy data is reactants minus products. And then we just want to count how many of each kind of bond we've got in the reactants, add them up, and subtract from them the total of the product bonds. Let's do that then. So here's the amounts of each type of bond we've got. So students often forget about this CO bond and this OH bond, especially when you're expected to draw these molecules yourselves. And now let's pop our numbers in. And I'm going to work out the total for the reactant bonds being broken first, and then the total for the product bonds being formed, and then I will subtract them. So we've got the total of the reactant bonds being broken and the total for the product bonds being formed. And we can see that since this number is larger, the reactant bonds being broken, our overall answer is going to be positive. So this reaction is going to be endothermic overall. The fact that this overall answer, the enthalpy change for this reaction is positive, that it's endothermic, this tells us that there are more reactant bonds being broken compared to new product bonds being formed. Let's have a look at this one then. It's a little bit different. So we've got the displayed formula for SO2 and SO3. It says the SO bond in those two molecules is not the same, and we're given some of the bond enthalpies. And it's asking us to calculate the SO bond enthalpy in SO3. It did give us a balanced equation. I appear to have chopped that off, but I've written it here. It was on a previous part of the question on a different page, but this is what we needed from it. So here's the balanced equation. It gave us a delta H value. So what we're finding is this, just in the SO3. So where do we start with that one then? Well, we start in exactly the same way. We set up our equation. Delta H, since we're given bond enthalpy data, it's always equal to reactants minus products. This time we're given the delta H value, so we can plug that in. It's always good to draw out our bonds from our balanced equations, so I'm going to go ahead and do that. So we've got 2 of this SO2, 1 lot of oxygen, and then 2 lots of this SO3. And now we can see all our bonds. So for the reactants then, I'm going to do it just like before. So I'm going to write down what I see first before putting the numbers in. Obviously you don't have to do that. It's just in case you're having a go yourself and you want to make sure that you've got everything. So in the reactants we've got 4 of this SO bond. Then we've got 1 of these oxygen-oxygen double bonds. And we're going to take from it the 6 SO double bonds. And these are the ones that we want to calculate. So we can start to pop our numbers in then. We can call this 6SO just like it is, or we can call it 6X, whatever you prefer. This is the unknown that we want to find out. And I'm going to start working these out and popping our numbers in. So since we're working out bond enthalpy, we know this 6x can't be negative. Bond enthalpies are always positive. So what I'm going to do next is make that whole term move across the equals. So it's going to change its sign to a positive. So it was minus 6x. That whole thing is going to move across the equals to change its sign. Same thing's going to happen with this one. That minus 196 is going to move across the equals to become plus 196. And this will stay where it was. Work that bit out first. 2778. Now remember that's the value for 6 of them. We just want 1 of them. So divide that by 6. And we get plus 463. And just make sure you write that on the answer line. And lastly, for bond enthalpy, something I always tell my students, remember bendomex. Bond breaking is endothermic, bond making is exothermic. Earlier we looked at how to find enthalpy changes through experiment. This is known as finding an enthalpy change directly, but sometimes that's not possible. Maybe the reaction is too slow, too dangerous, or creates unwanted side products, and that is when we use Hess's law. Hess's law allows us to find an unknown enthalpy change indirectly by linking a particular reaction to alternative pathways with known enthalpy change values. Hess's law states if a reaction can take place by more than one route and the initial and final conditions do not change, then the total enthalpy change is the same for each route. In simple terms, route 1 is equal to route 2. One of these routes is always the direct route, whereas the other one is the indirect route. Imagine you want to fly from Birmingham to Rome. You can get a direct flight, and this is your direct route. We can call this route 1. Or you can go via Amsterdam and get a connecting flight. This would be your indirect route, and we can call it route 2. Although the routes are different, we're still starting in Birmingham and finishing in Rome in both routes. Hess's law is similar. A reaction can happen in one step, the direct route, or several steps, the indirect, but the overall enthalpy change is the same, since it depends only on initial and final states, in other words reactants and products, not on the pathway taken. Now let's look at the two common types of Hess cycle you're likely to need in Year 1. Hess cycles are visual diagrams used to link a particular reaction to an alternative pathway in order to calculate an unknown enthalpy change. Previously, we looked at the different types of standard enthalpy changes. Enthalpy changes of combustion and formation are often used in order to find an unknown enthalpy change, and that's what we'll look at here. There are two types of Hess cycle that you're likely to come across in Year 1. The one we use depends on the type of enthalpy data that we are given in the question. Let's look at some exam questions then. Our first one, we are given enthalpy change of formation data. See that little F there? So that means if we are going to draw a cycle, it will be this one that we use. So I'm going to show you two ways to get the right answer. The way with the cycle and the way where we use an equation instead. Now at the bottom we'd have the elements, or we can just write the word elements. I mean, we don't have a mark for drawing the actual cycle, but just to show you how it would look, I'll pop the elements in. And then we balance, it just balances with one side. So 2 nitrogens here, 4 hydrogens there, and 6 oxygens. And then that's balanced with this side and that side. So this is the unknown enthalpy change that we want to find, the enthalpy change of combustion, and we're going to use this formation data to do it. So the first thing we're going to do is identify our two routes. Now, there's more than one way to do this. The way I like to do it is to look at the direction of the arrows. So we've got two arrows going in the same direction clockwise. I'm going to call that route 1. And we've got one arrow going anti-clockwise, and I'm going to call that route 2. And because route 1 and route 2 are equal to each other in terms of the overall enthalpy change, it doesn't matter if we call this one route 1 or this one route 2, because they're equal. Next thing I'm going to do is collect the terms involved in each of the two routes and write them equal to each other. So I'm setting up an equation. So you can see we've got one hydrazine that's involved in route 1 and its value is 50.6. The value for enthalpy change of formation of oxygen is 0, and that's because it's an element in its standard state. So there's no enthalpy change of formation values for elements, they're all 0. The unknown enthalpy change is also part of route 1, so we'll pop that there. Then in route 2 we've got 2 NO2. So 2 times this value plus 2 lots of water. Now I'm going to pop this bit in my calculator first and work out what this equals. So I've got minus 505.2 for this side over here, 50.6 plus the enthalpy change of combustion. I want to rearrange to make this the subject, so that means I'm going to move this over the equals and it's going to become minus 50.6. Because when we change sides, we change signs. And I've got minus 555.8, which is A. Now I said I'd show you another way to do it. So whenever we're given formation data, we can either use this Hess cycle method, and you can do it like I've done it. Route 1 is equal to route 2, or maybe your teacher or you've seen online someone else has taught it a different way. Use whichever way you prefer. As long as you understand it, feel comfortable with it, and it gets you the right answer, use the one you prefer. The other way we can do it is just to use an equation. So whenever we've got formation data, we can just do products. So 2 times NO2 plus 2 times the value for water minus reactants. So take away this hydrogen value and then the oxygen is 0. So if you did want to try that, have a go and you'll get exactly the same answer. Let's do another one then. So this time we've got combustion data instead of formation data. So whatever cycle or equation we use always depends on the data we're given. So since we've got combustion data, I'm going to draw the cycle just so you can see how it would be. We don't have to draw the cycle. We can just do it like this or use the equation. So for combustion, this time it would be reactants minus products. So remember, it would be this one this time. I'm feeling lazy. CP for combustion products. We're not going to get a mark here for balancing our equation, neither would we there, because it was only multiple choice anyway. If it did ask you to draw the Hess cycle, then we would need balanced things here, so CO2 and water with state symbols, but it's not asking us for that. So here's the unknown enthalpy change, and I'm going to do the same method as before. So I'm following the arrows. These two are going clockwise, that's route 1. This is going anti-clockwise, I'll call it route 2. I'll apply Hess's law, so Hess said route 1 equals route 2, and now I'm going to collect my terms involved in each route and write them equal to each other. So in route 1, I've got the unknown delta H that we want to find. Oops. I've also got this one, so butane, which is minus 2877. I've also got 2 lots of propene. And then in route 2, I've only got one thing, decane. So I'm going to work out what this gives on my calculator first. So I end up with this, delta H plus minus 6993 equals this. Now I want to move this over the equals, so it goes from being a minus to being a positive once it moves over the equals. So you can see we're going to end up with a positive enthalpy change because this number's bigger. So the enthalpy change is positive 215. And if you did want to try the equation method, it's reactants minus products. So the value for decane, take away the value for butane and the value for 2 of the propene. For those of you who did want to see one more example, let's do this one. We've got formation data. This time I'm going to show you the equation method. So we've got our products here, we've got our reactants here. So I'm going to do products minus reactants. Got 2 of the nitric acid. We've got 1 of this. And for the reactants, we've got 1 of the water. And we've got 3 NO2. Now, whenever we end up with a minus minus, that makes a plus. So the correct answer is minus 136.5, which is B. So that's how we use the cycles and the equations to get our answer for the unknown enthalpy change. And notice, depending which type of data we are given, The equation flips, so if we're given formation data, products minus reactants. If we're given combustion data, reactants minus products, and that's because the arrows flip on the cycle. I hope you found that helpful. If you did, please like and subscribe for more videos. Thank you for watching. Bye.